odd powers, everything is totally straightforward because the odd power functions are one-to-one. The even power functions are not one-to-one. And we were able to get an idea of an even root by restricting the domain of our even power functions. But that results in a complication when we try to use even roots to solve equations. There was a possibility of having a positive root, which is the one we took, and also the possibility of having a negative root, which we didn't use. So if we have an equation where a positive power function is equal to some number, then the input of that power function is either equal to the positive root or to the negative root. When we use an even root to eliminate an even power, we have two possibilities, the positive root or the negative root. Also notice that our number here, the number we're taking this even root of, has to be non-negative because we can't take an even root of a negative number. If we have a negative number, this equation just kind of straightforwardly has no solution. The good news is we can recognize that has no solution and stop. The bad news is we have an equation with no solution. Now, this move, where we have the positive root and also the negative root, we'll sometimes shortcut that by writing this plus or minus sign. Right, we see this sign and we read it as plus or minus. And the reason that we'll take that shortcut is that then we can do the remaining steps only once and combine everything at the end. So, how do we solve an equation using this even root property? Well, we isolate the something to a power equals a number. We apply the even root property to rewrite, if possible. So if the even root is going to be defined. And then we finish solving. Let's see a couple of examples of this in action. In this first example, we have x to the fourth equals 16. So my power expression is already isolated. It's already by itself on one side of the equation. Next, I'm going to apply the fourth root property. So either x is the fourth root of 16, or x is the negative fourth root of 16. Actually taking the fourth root, we get x is 2, or x is negative 2. Plugging both of those solutions into check, 2 to the fourth really is 16. Negative 2 to the fourth also really is 16. Okay, so two solutions, x is 2 or x is negative 2, and we're now finished. In this next example, we have a power expression that is not yet isolated. So to isolate this, we need to get rid of this 2. We'll divide both sides by 2. So on the left, we'll just be left with 2x plus 1 squared. On the right, 50 divided by 2 is 25. Next, we'll apply the even root property. Now, I'm going to use the plus or minus shortcut at this point, and we'll see some of the benefits and some of the drawbacks of using that shortcut. So 2x plus 1 then is plus or minus the square root of 25. In other words, plus or minus 5. Now we need to continue solving for x. And to do that, first we want to subtract 1 on both sides. This is the major drawback to using the plus or minus shortcut. I can't combine that 1 and that 5, because I don't know whether I'm going to do plus or minus. So here I'm going to split up because now I have 2x is -1 minus 5 is -6, or 2x is -1 plus 5 is +4. Right? I wanted to combine those before I divide by 2, because now I'm going to take -6 divided by 2, and I get x is -3. Or I take +4 divided by 2, and I get x is 2. Right? So that plus or minus shortcut can make our next writing steps faster, but it means that we can't combine things, and it might make for some ugly arithmetic. All right, let's check that this really worked. So for x is -3, we'll have 2 times -3 plus 1 squared is 50. Looking inside the parentheses, we're going to have -5 squared. I think that's going to be fine. And throwing that into a calculator, it does all work out. With +2, we'll have 2 times 2 plus 1 squared. So inside the parentheses, we'll have a 5. That seems reasonable. And throwing everything into the calculator, that also works out. So each of our solutions actually worked in that equation. Okay, let's see one more example where something goes wrong. Here I have x plus 3 to the 6th power equals -1. That can't happen, right? If I take the 6th power, I always get a positive number or 0. So looking at this equation, I can immediately see that it has no solution. I don't need to do any steps at all, because I can look at that equation and see that it has no solution. Once the power expression is isolated, if you see your power expression equals a negative number and it's an even power, you know it has no solution. Now, just like with the odd powers, we can solve these equations as polynomial equations if we're lucky. So for example, x to the 4th equals 16. That's a polynomial equation we know how to solve. So I'm starting with x to the 4th is 16. I'll subtract 16 on both sides. So x to the 4th minus 16 is 0. That's a difference of squares. I'll have x squared minus 4 times x squared plus 4 equals 0. But then x squared minus 4 is still a difference of squares. X minus 2, x plus 2, x squared plus 4 is equal to 0. So that means either x minus 2 is 0, x plus 2 is 0, or x squared plus 4 is 0. I think it's pretty easy to see that this one can't happen. Right? X squared is always positive. If I take something positive and add 4 to it, I'm not going to get 0. X minus 2 is 0. That means x is 2. X plus 2 is 0. That's x is -2. Notice those are the same solutions that we got with the even root property. So again, if we can solve it both as a polynomial equation and as a power equation, we'll get the same solutions. Usually taking the roots is going to be the easier way.